Have you ever wondered if time travel could be more than just a science fiction trope? It's a question that has tickled our collective curiosity for generations. From H.G. Wells's The Time Machine to Back to the Future, time travel has been a staple of pop culture, a fascinating concept that has fueled countless stories and stirred our imaginations. But what if we told you that this seemingly fictional concept has roots in real science? That's right. Time travel isn't just a figment of the creative mind, but a topic of serious scientific inquiry. From the abstract realms of theoretical physics to the concrete experiments in labs, scientists have been exploring the mysteries of time for years. One name that stands out in this quest is Professor Brian Cox, a renowned physicist and science communicator. Professor Cox, with his charismatic persona and lucid explanations, has made complex scientific concepts accessible to the masses. But more importantly, he has brought the question of time travel from the realm of science fiction to the forefront of scientific discourse. Indeed, Professor Cox has not just talked about time travel, but he has conducted a groundbreaking experiment that has had the scientific community buzzing. This experiment, which we will delve into in more detail later, has challenged our conventional understanding of time and its linear progression. It has opened up new possibilities, new questions, and maybe, just maybe, a new reality where time travel is more than a dream. But before we uncover the details of this mind-bending experiment, let's take a moment to understand what makes time such a complex concept. Time, as we perceive it, is linear. We move from the past through the present into the future. But is that all there is to time? Or could there be more to this seemingly straightforward dimension than meets the eye? So what exactly did Professor Cox do to shake up our understanding of time travel? Hold on to your seats, ladies and gentlemen. We're about to take a journey into the heart of time itself. To explore the reality of time travel, Professor Brian Cox didn't need a flashy DeLorean or a fancy time turner. Instead, he turned to one of the most famous equations in the world, EMC squared. This equation, courtesy of Albert Einstein, is the backbone of modern physics. It's a simple, yet profound equation that stands for energy equals mass times the speed of light squared. Now let's break it down a bit. The E stands for energy. Everything in the universe, from the smallest particle to the largest galaxy, contains energy. The M stands for mass. This is the amount of matter in an object. And C squared, that's the speed of light squared, a truly astronomical figure. But what has all this got to do with time travel, you ask? Well, the beauty of this equation is that it ties together energy, mass, and the speed of light, and by extension, space and time. According to Einstein's theory of relativity, as an object moves faster, time slows down for it. This is known as time dilation. So how did Professor Cox use this equation to demonstrate the possibility of time travel? He used the simple and elegant concept of a light clock. Imagine a light beam bouncing between two mirrors. Now, if the mirrors start moving at near light speed, the path the light beam takes becomes longer. To an observer moving with the mirrors, the light beam still bounces back and forth at the same rate. But to a stationary observer, the light beam appears to take more time to bounce back and forth. In essence, time is slowed down for the moving light clock. It's experiencing time dilation. By using the principles of EMC squared, Professor Cox demonstrated that if we could travel at near light speeds, we could, in theory, travel into the future. Quite a concept, isn't it? But how does that translate into time travel? To understand Cox's experiment, we first need to grasp a few key concepts about time. Time, as we perceive it, is a linear progression, a constant march from past to future. However, in physics, time is a much more complex and intriguing concept. One of the groundbreaking theories that revolutionized our understanding of time was Albert Einstein's theory of relativity. The theory of relativity posits that time is not an absolute entity, but rather a relative one. This means that time can be stretched or compressed depending on certain factors, leading us to the fascinating concept of time dilation. Time dilation is a difference in the elapsed time measured by two observers, due to a relative velocity between them or to a difference in gravitational potential between their locations. In simple terms, it means that time can run faster or slower, depending on how fast you're moving or how strong the gravitational field is around you. To illustrate, imagine you're on a spaceship, traveling close to the speed of light while your twin sibling stays on Earth. According to the theory of relativity, when you return to Earth, you would find that your twin has aged more than you have. This is because time has been moving slower for you on the spaceship due to your high speed. This is an example of time dilation due to relative velocity. Similarly, if you were to spend time near a massive object, like a black hole, where gravity is extremely strong, time would also slow down for you relative to someone far away from the gravitational field. This is an example of time dilation due to gravity. These concepts are not just theoretical constructs, but have been experimentally verified. For instance, accurate atomic clocks on satellites in space run slightly faster than similar clocks on Earth, due to both the velocity and gravitational effects. Now that we have a better understanding of time, let's delve deeper into Cox's experiment. So, Cox has shown us that time travel is theoretically possible, but what does that really mean for us? Let's break it down. Essentially, Professor Brian Cox's experiment has opened up a universe of possibilities, quite literally. If time travel is possible, even just in theory, it means we might someday have the potential to move backwards and forwards in time, to witness events that have already happened, or to see what's yet to come. Imagine being able to visit the age of the dinosaurs or see what the future holds for humanity. But it's not all smooth sailing. There are significant challenges that remain. For starters, the technology required to make time travel a reality is far beyond anything we currently possess. We are talking about energy requirements that would dwarf those of any project undertaken by humanity so far. And then there's the question of safety. Would time travel be safe for humans? Could we survive the journey through time without negative impacts on our health or even our very existence? Furthermore, there's the issue of paradoxes. What would happen if you traveled back in time and changed something? Would it create a new timeline, or would it affect our present? These are complex theoretical questions that we don't have answers to yet. Then there's the ethical dimension. Who gets to decide who travels in time and to what period? What if time travel was used for nefarious purposes, to change history for personal or political gain? These are serious considerations that we must grapple with as we ponder the implications of Cox's experiment. In essence, while the theoretical possibility of time travel is tantalizing, the practical application is still a long way off. We are only at the beginning of understanding the complexities of time and the universe. It's like standing at the edge of a vast ocean, knowing there's an entire world beneath the waves, but not yet having the means to explore it. So, while we may not be hopping in a time machine anytime soon, Cox's experiment has certainly given us food for thought. Time travel, once the stuff of science fiction, has been brought into the realm of possibility by Professor Brian Cox. In our journey today, we've seen how this trailblazing physicist has turned the fantastical into the feasible, challenging our perceptions of what we believe to be possible. Let's recap the key points of Cox's experiment. It all started with a simple question. Can we move through time as we move through space? To answer this, Cox turned to Einstein's theory of relativity, which suggests that time is not a constant, but rather, it is influenced by speed and gravity. His groundbreaking experiment demonstrated that time can indeed be manipulated, offering a glimmer of hope for potential time travelers. But what does this all mean? What are the implications of Cox's experiment? For one, it challenges our basic understanding of time as a linear, unchanging entity. If time can be manipulated, then our perception of past, present, and future may need to be revised. Moreover, if we can move forward in time, could it also be possible to move backward? These are questions that have yet to be answered, but thanks to Cox, we are one step closer. The broader impact of this research extends beyond just time travel. It also has significant implications for our understanding of the universe. If time is not fixed, then neither is the universe. This opens up a whole new world of possibilities, from parallel universes to alternate realities. In conclusion, Cox's experiment has not only brought us closer to understanding time travel, but it has also expanded our knowledge of the universe and its workings. As we continue to push the boundaries of what we know and understand, we unlock new doors to discovery and innovation. And so, as we wrap up our exploration of time travel, we are left with a sense of wonder and anticipation. As we continue to unravel the mysteries of the universe, who knows what other science fiction concepts may one day become science fact?